All right, welcome to the Explainer. Today, we're getting into circuit breakers and basically uncovering what senior engineers know that most developers really don't. We're going to shatter a huge myth that absolutely plagues our industry right out of the gate. This whole illusion that more code somehow equals a better engineer. Listen, if you've ever felt that burning urge to write some massive, overly complex framework just to prove your technical chops, yeah, you need to hear this. We're diving deep into the harsh realities of hyperscale systems, the actual literal cost of stability, and the architectural secrets that really separate the rookies from the battle-hardened seniors.
So let's start with a really hard truth. I like to call it the deletion paradox. Think about it. When a junior developer joins a team, right, they desperately want to prove themselves. So what do? They add features, they add validation layers, utility functions. If you look at their code contribution graph over a year, it literally looks like a mountain range. But when a true senior developer joins that exact same team, man, in their first month, they might just delete 15,000 lines of code. They're in there ripping out unused microservices, consolidating redundant functions, just dropping heavy, useless dependencies. Their contribution graph looks like a massive valley. And honestly, guess which developer the company values more? The senior engineer gets the promotion, and it's because they understand one fundamental, undeniable rule. Every single line of code is a liability. Seriously, code breaks. It demands maintenance. It introduces these terrifying subtle bugs the second a dependency updates. But most importantly, it adds massive cognitive load for the next poor soul who has to read it. You know, our brains can only hold so much context at once. Senior engineers know that simplicity always beats sophistication. The absolute best code, it's the code that doesn't even exist.
And you see this philosophy extend directly into how we design our systems. Take AI agents or complex workflow systems, for example. The rookie mindset tries to engineer this bulletproof solution that automates 100% of edge cases. They build this absolute tangled web of conditionals, just trying to predict every single possible failure. But a mature senior design goal, it's way more honest. You aim to automate the 90 to 95% of cases the system can actually handle with confidence. And for the rest, you escalate them. You kick them over to a human or toss them into a dead letter queue, basically a secure holding pen for failed events, with all the context attached. You just have to stop trying to code your way out of unpredictable chaos.
Okay, let's dive into this with a really practical example. Look at API contracts between, say, a front-end mobile app and your backend. A rookie is going to build strict JSON mapping right into their client, meaning if the backend makes a tiny mistake and drops a single non-critical field, bam, the strict parser throws a fatal error and the entire app just crashes for the user. A senior engineer, though, they follow the permissive parser rule. They're robust in what they accept. By using optional types and safe navigation, if a field is missing, the app just gracefully degrades. Maybe it just shows a blank space instead of a terrifying crash screen. You are literally saving the user experience just by expecting things to fail.
Which brings us to Section 1, Distributed Systems Are Broken. The reality of scale. Look, the second you move beyond a simple monolithic app, the basic rules of physics just change. Welcome to the reality of hyperscale. To really wrap your head around this scale, think about Uber. A single ride-hailing request doesn't just hit one web server. No way. It traverses something like 500 discrete microservices and kicks off over 30,000 remote procedure calls. I mean, at this level of interconnection, you are dealing with a completely combinatorial explosion of failure modes. Even a minor network hiccup in some random, non-critical downstream service, if you aren't careful, that can cascade and take down your core business functionality.
And in these wild environments, traditional monitoring just doesn't cut it anymore. Monitoring is great for your known unknowns. You know, the things you actually expect might break, so you slap a CPU or a memory dashboard on them and call it a day. But distributed systems, they are entirely dominated by unknown unknowns. These are bizarre emergent failure modes you couldn't have imagined in your worst nightmares, like a subtle clock skew causing a silent ordering bug. Or, hey, a configuration change in service A suddenly causes service B to aggressively retry, which then ultimately crashes service C's database connections. No individual health check actually fails, but the entire system is completely degraded.
All right, moving to Section 2, real-world panic moments. To really grasp the gravity of this, I want you to step into the post-mortem room with me. We're going to look at some actual real-world production nightmares. You know, the kind of catastrophic failures that leave permanent scars on an engineering team.
First up on the slab is the retry storm, sometimes called the butterfly effect. Picture this. You have a localized failure. Maybe a simple database query times out. Simple enough, right? But what happens next? Well, the client automatically retries.
But if thousands of clients all retry at the exact same millisecond, you've just created an exponential, massive growth in traffic. It plays out exactly like this, step by step. First, that localized failure happens. Second, the clients retry blindly. Then, suddenly, the upstream service isn't just dealing with its original degraded performance, it's getting absolutely hammered with double, triple, or quadruple the normal traffic volume. This massive spike exhausts the thread pools, which triggers more timeouts, which leads to, you guessed it, more retries. The cycle just accelerates until the entire cluster is literally collapsing under the sheer weight of its own error-handling logic. And let me tell you, trying to add more code to fix the timeout in the middle of this, you were just pouring gasoline on a fire.
And unfortunately, that is just the start. Let's rapid fire through some other real-world battle scars. How about a non-atomic database migration that times out halfway through? You try to roll it back, but boom, you're trapped in a zombie state. The column exists, sure, but only 40% of the rows actually have data, and your app is crash looping because it expects an all-or-nothing state. Or what about the hot pod scenario? Your load balancer is working perfectly, but a single massive 30-second API call comes in and completely locks up 100% of a pod's CPU. Or, and we have all been here, the ultimate facepalm, a staging deployment pipeline that, thanks to some sloppy VPC peering, is physically executing flush commands against your production Redis cluster, wiping out your live cache. Look, relying purely on the happy path leads directly to these crises.
So, how on earth do we survive this? Section 3, the Senior Architectural Toolkit. Spoiler alert, we don't survive by writing clever algorithms. We survive by deploying specific, blunt force architectural patterns.
Consider this your ultimate survival gear. First, circuit breakers. These physically stop those retry storms by tripping and failing fast when an upstream service degrades. We combine these with model fallbacks, like if your main AI API is throwing 500s, you automatically route to a cheaper, smaller backup model. Next, we use back pressure. That's how we tell clients, hey, slow down, I cannot handle this load right now. We also enforce strict distributed deadlines, so a timeout doesn't just waterfall infinitely across 15 different microservices. And for those massive hotpot API calls we just talked about, we literally stop using synchronous HTTP entirely for them, and we offload that heavy work to a background job queue, like SQS. And this brilliantly illustrates the mindset shift. Look closely at this matrix on the screen. This is mapping out how large-scale internet services systematically defend against outages. I want you to notice the columns focusing specifically on redundancy and isolation, because they aren't just crossing their fingers and relying on writing bug-free code. That's impossible. Instead, they are explicitly utilizing redundancy, enforcing strict component isolation, and doing continuous online fault testing. They literally proactively inject faults into their live systems just to ensure these circuit breakers and isolation boundaries actually work in production. It heavily mitigates operator and hardware errors before they take the company offline. Let's zoom in on one of the most powerful tools in that toolkit, idempotency. Just look at this staggering number, over $640 billion. That is Stripe's annual processing volume. And honestly, it is successfully protected from catastrophic double billing entirely by the rigorous use of idempotency. Here's how it works. In a distributed system, a network call might actually succeed on the server, but then the network blips and the response drops before it ever reaches the client. So the client naturally retries. If you don't have an idempotency key, guess what? You just charge that customer twice. That's a nightmare. So Stripe forces clients to send a unique ID with every single mutation. They store this key in Redis with a 24-hour time to live. If they see that key again, they don't process the charge. They just return the cached success response. Airbnb actually takes this a step farther. They hash the booking parameters alongside the key, which completely prevents malicious users from trying to reuse an old key to book completely different dates. It is just absolutely brilliant defensive engineering. All right, moving on to section 4, the trade-off trap. Now here is exactly where we separate the mid-level developers from the true seniors. Because integrating all these safety mechanisms, it elevates us into the very mature practice of managing architectural trade-offs. I really want to pose this question directly to you. What is the true cost of stability? Think about it, because every single layer of safety, every circuit breaker, every redundant volume you add to a system, it extracts a massive, unavoidable tax. You simply do not get stability for free. Let's actually look at the receipts here. Say you want the hardware safety of AWS EBS read-write-once volumes. Great. But the cost is that during a node failure, Kubernetes is going to take exactly 6 minutes to safely detach and reattach that volume, which significantly degrades your recovery time objective. Okay, what if you want guaranteed application stability in Kubernetes by setting your memory requests equal to your limits? The cost there is sacrificing bin packing efficiency. That means you are going to waste literally millions of dollars paying for unused RAM across 10,000 pods. Oh, you want proactive connection leak detection? Well, capturing those stack traces is going to cost you a 1 to 2% CPU overhead penalty globally. These are the hard, expensive choices that senior engineers have to make every single day.
Which brings us to our final section. Section 5, mitigate now, investigate tomorrow. Let's talk about what actually happens when the pager goes off at 2 a.m. and all these safety nets fail. Because your operational philosophy during incident management, that is the ultimate test of a senior engineer.
So the crucial point is this: when everything is literally on fire, your ego naturally wants you to find the bug, write a clever fix, and deploy it immediately to save the day. A rookie will absolutely attempt a forward fix during a massive outage. But a senior knows that writing and testing code under the massive adrenaline rush of a P1 incident is a terrible, terrible idea. It almost always introduces a secondary, even worse bug. Your only job during an outage is mitigation. Just roll back the deploy, flip the feature flag off, route your traffic to a completely different zone, stop the bleeding today, investigate the actual root cause tomorrow when everyone is awake during normal business hours. As the legendary engineering leader John Allspaw once noted, mature engineers do not practice cover-your-ass engineering. They don't walk around pretending their code is flawless. They spell out the trade-offs right at the onset. They know that corners absolutely have to be cut to ship product, so they actively plan for those failures. They accept the responsibility, they build in the fallbacks, and they recognize that managing the sheer messiness of the real world, well, that's the very definition of good engineering. We have covered a lot of ground today, from retry storms and distributed system nightmares all the way to the very real, costly trade-offs of stability. But I really want to bring it all back to where we started. Before you sit down to design that next massively complex microservice, or before you add yet another library just to handle some bizarre edge case that might not ever happen, just stop. Look at your architecture and ask yourself, what code can you delete today? If you're ready to start building like a true senior engineer, share this explainer with your team, drop your most massive code deletion win in the comments below, and don't forget to subscribe for more deep dives. Thank you so much for watching, and I'll catch you in the next one.